Okay, good morning. Let us get started.
Good morning, sir.
Good morning. Okay, so let us just try to recap what are the things that we have done in the first two classes. Can you tell me what important things we have done or what concepts we have talked about in the first couple of classes? Somebody can tell me.
So we
Unit
studied
conversion.
about
Yes, one of the things we talked about is conversion of units. Have you done homework?
yes, sir.
Yes.
Yes, sir.
Fairly
Yes, sir.
straightforward. Okay. Anything else that we learned?
Considering a basis for the
Right.
calculation.
Right. So we talked about basis.
Compositions.
Yes. So basis was our that is our start point for our calculations. Then we talked about different ways of expressing compositions. We talked about weight percent, weight fraction, if you like, multiply that by 100, will give you weight percent, mole percent, volume percent. We talked about molarity, we talked about molality, normality, parts per million by weight. It could be parts per million by moles, right? All these different ways of expressing compositions in a mixture or in a solution. We talked about those. What else did we do?
So we talked about using the ideal gas law.
Yes. So the next thing that we did was looking at ideal gas law. So what the gas laws are going to do is going to relate the pressure and volume to temperature and the gas constant R. We talked about different units of R. So we said that it was 8.3. We said the unit was 8314 joules per kilomole Kelvin, or you might be commonly using 8.314 joules per gram mole Kelvin. Yeah. Anything else we did?
Error and significant figures.
Beg your pardon, say that again.
Errors.
Error and significant figures.
Errors, right? Significant digits. When I represent something, some quantity as, let's say 45.382, 38369 or 79, whatever, 5428, right? What I'm saying is that my accuracy is up to this decimal place, isn't it? Whereas our measurement accuracy of that quantity would be not that accurate. It may be plus or minus 5%, plus or minus 2%, depending on what method or what instrument we are using. Correspondingly, there's no point is, suppose we are talking about length in centimeters, there's no point in talking about so many units because we can't measure length up to what, how many, 2, 4, 6, 8, 10 decimal places, right? So our measurement accuracy is not in picometers. So we might as well round it off to just say 45.4 centimeter. That means our measurement accuracy is plus or minus 1 millimeter, right? That's what you will get when you are using a scale. You can't measure anything below the third significant digit or first decimal place. Okay, so be very careful about calculating and reporting all these, right? So don't just report all the numbers because of your calculator gives so many digits, and don't worry about answers. Some of you might have a fear from your 12th standard or 11th standard or 10th standard that if your answer is 43.38471, And if my answer is 43.384720, you will get 0, and only persons with this will get 10 out of 10. No, it is not like that. In fact, if you write so many decimal places, I will give you a 0. Okay, so don't think that you are going to lose marks by rounding off. So we should always round off our answers. Okay, anything else we learned?
Sir, absolute and gauge pressure.
Right, excellent. Absolute pressure and gauge pressure. Very nice. What else?
Sir, process block diagrams.
Process block diagrams, right? Yes. Block diagram. It's understood that it's a process block diagram. One more thing I had asked you to revise about
pH.
pKa, pH, all those things. Have you done? Anybody has any doubts based on that? Yes, please ask.
Sir, is hydrolysis also included in that?
Hydrolysis means what? What do you mean by hydrolysis?
So salt hydrolysis equation.
So give me an example.
So the hydrolysis of a salt of a weak acid and a weak base.
Weak acid and a weak base. What is that? Which salt are you talking about?
CH3COONH4.
Okay, hydrolysis of weak acid and weak base. Okay, now so in presence of water it will get hydrolyzed to or dissociated into these. That's what you are saying, right?
Yes, sir.
Yeah. So all those things are related, right? Because this is coming from where? This is coming from two different equilibria, right? And NH4OH, all these equilibria are related, right?
Yes, sir.
So these two equilibria and this equilibria, they are all related to one another because our H plus into OH minus ions is 10 raised to minus 14. Isn't it? So yes,
sir.
Yes, this is just an extension of all of this. Right? Sometimes we may have multiple equilibria. Good point that you have raised. It just reminded me of something else. Say, for example, we have carbon dioxide dissolved in water. Right? So there are two equilibria. You have H plus and HCO3 minus bicarbonate, and your bicarbonate is also going to dissociate further into the carbonate and another H plus. So you have two replaceable H plus ions or two replaceable hydrogens. So we have two equilibria. So you have pKa1 for the first dissociation, pKa2 for the second dissociation, right? Or if you take phosphoric acid, there are three exchangeable hydrogen ions. So you have pKa1, pKa2, right? And similarly pKa3. So there are three such exchangeable protons. So we will have pKa1, pKa2, pKa3. Now, some of these things become very important when you want to neutralize something. Let's say we want to neutralize some base using phosphoric acid. Then depending on what pH we neutralize, we will get the corresponding salt. Right? So corresponding to pKa1, pKa2, pKa3, we will have the corresponding only first dissociation happening, or both first and second dissociation happening, or first, second and third dissociation happening. So depending on what pH we stop this titration process, we will have different salts that are formed. Do you agree? Do you disagree? Especially,
Agreed, sir.
yeah, especially because, let's say for example, things like citric acid, again, three replaceable H plus ions, and then you can make different salts of citric acid. So you can have a tri-basic salt, you can have a di-basic salt, you can have a mono-basic salt, depending on what pH we stop our neutralization. And the degree of dissociation, so typically if you are talking about, let's say, carbonate ions, so if you think about the carbonate ions, if you go to very high pH, then even the second dissociation will happen. So so for example, if you plot, let's say for example, pH versus let's say degree of dissociation. Ever done these kinds of calculations in 11th, 12th standard? No?
No, sir.
Okay, so they are just based on, maybe we will try to do an example in the next class. Okay, so imagine that we have let's say let's take carbonate, okay. And if you think about pH 7, and as you keep on making it alkaline, you will have corresponding to pKa 1. Now don't bother mugging up these pKa values, but you can just look up any source. One of the good source for all these kinds of pKa values for different acids and different bases is a source called as Handbook of Chemistry and Physics. It has data on variety of constants that are commonly used in chemistry and physics. So these are dissociation constants. So one of the chapters, it's a very big book. One of the chapters, one of the sections in the chapter is related to the values of pKa1, pKa2, pKa3 for different acids and different bases. So if you, let's say, stop at around pH 9 or pH 10, you will have essentially bicarbonate ions present. And so let's say maybe practically almost 100% bicarbonate ions, and practically negligible carbonate ions. Why? Because the second dissociation constant, the pKa2, we have not yet crossed that particular pH. Whereas if you go to pH 12, 13, then you will have negligible carbonate ions, negligible bicarbonate ions, and practically 100% carbonate ions. Right? So depending on the pH, you will have, you can get a bicarbonate salt of a base, or you can get a carbonate salt of a base. So you have a sodium bicarbonate or sodium carbonate. Right? Sodium bicarbonate we keep on eating and consuming as a food item. Sodium carbonate, don't even think about consuming, isn't it? So yes, all these are same concepts, just related to different things or different implications. So just to give you a example, we will try to do a problem based on these multiple dissociations for an acid, or multiple dissociations or multiple neutralizations of salts. So okay, so this problem we will do slightly later. Let's not go into this just now. So this I'll just make a note of it. So I'll give you the data and I will make a problem, and then we'll solve. Okay, anything else? Any other concept? Yes.
Sir, what will happen if we consume sodium carbonate?
Sodium carbonate is highly alkaline, right? So you will, it's not edible. You will feel nauseated, as if you are drinking sodium hydroxide. It's like that.
Yes, sir.
Don't try.
No, sir.
So who's saying that? Nishant, are you saying that? Don't experiment.
So
Rishabh, don't experiment.
Yes,
sodium bicarbonate you can eat as much as you like. Sodium carbonate, don't even think. All right. Shall we go to a problem now?
yes, sir.
Yes, sir.
Okay, so here is one problem. Okay, let's take this problem. Reverse osmosis to make potable water. Okay. Imagine that we have seawater. So let's say seawater contains 3.5 weight percent sodium chloride. Rest water. It contains many other minerals as well, bromine and other minerals, but let's not worry about that just now. So it is sent to a membrane. That membrane process is called as reverse osmosis. What we get, so there is a membrane like this. Water permeates through the membrane. So we get a water stream containing, so this is like a potable water. You can drink this. So these kinds of modules are there in your homes as well. These water purifier machines, they sell all these machines which are RO based. So they remove the ions. So this is the water that you drink. It goes through the membrane, but it stops the salt from going through the membrane. So let's say this water that is drinkable, let's say it contains 0.1 weight percent sodium chloride and rest water. Now, what remains on the other side of the membrane is a enriched salt content in the water. So let's say in this particular case, sodium chloride is 8 weight percent sodium chloride and rest water. Okay, is everybody able to visualize the problem? We have seawater which contains 3.58% sodium chloride, rest water. We send it to a membrane. What permeates goes through the membrane. Permeates means goes through the membrane, is essentially pure water, but it has small amounts of salt, let's say 0.1% sodium chloride and rest water. This is what you drink. This is what the water purifier machines in your home do. And there is a reject. So this is called as a permeate, something that goes through the membrane, and something that is retained on the membrane is called as a reject or retentate, retained on the membrane. Okay. So let's say the retentate is or reject is 8 weight percent sodium chloride and rest water. Okay. So I want you to calculate kgs of permeate solution per kg of incoming seawater. So in your water purifier machine at your home, there's no seawater, it is just already purified water. So, but these kinds of things are done very commonly on ships. So when the ships sail for long months and weeks, they don't carry all the water required for the people on the ship. They generate water for drinking purposes by reverse osmosis plants installed on the ship. Okay, so let's calculate this. I'll give you 5-10 minutes to complete this. Once you have completed, tell me your answer. Everybody's understood the problem? Anybody who's not understood what is to be done, what is to be calculated? Has everybody understood what is to be calculated? Anybody who has not understood what?
Yes, sir.
Yeah. Anybody has answers? Anyone has answers? No?
Sir, 0.5696.
So
Yes, sir.
0.569
kg.
kg.
569. So let's just say 57. Okay, 1, 2, 3 answers I think so far.
So yes, sir, 0.57.
Okay.
Sir, can I ask a small doubt
Yes, yes, please.
in the homework one?
Yes, yes.
Sir, 1 Fahrenheit, the one change in Fahrenheit equals to, sorry, the 1 Kelvin change is equals to 1.8 Fahrenheit, sir.
Correct,
Is it right?
correct, correct, correct.
Thank you, sir.
Yes, sir. 0.57.
Yes. We just wait for some more people to answer.
Yes, sir, 0.57.
Okay. Anybody else? Any other answer?
Yes, sir, 0.57.
Okay. Other people want some more time, or should we see the solution? This seems to be very popular answer. Maybe it is correct. Other people want more time? Or should we see the solution? Okay, let's try to see the solution. Maybe some of you are stuck, maybe some of you have got a different answer, doesn't matter. What we are going to do in the solution, first thing that we are going to do is our process block diagram, right? In this particular case, the process block diagram I have already given, isn't it? So we are going to draw a block diagram so that it helps us to visualize the problem. It helps us to visualize what is coming in, what is going out in terms of materials, catalyst, chemicals, energy, all those things, and what is going out in terms of reject, in terms of waste, in terms of product, in terms of byproduct. So we are always going to start with a process block diagram. That is the first and foremost thing. In this particular problem, I have already given to you the process block diagram, that yes, there is a block which is reverse osmosis. That's the process that is happening. Input to the process is our 3.58% seawater, 3.58% sodium chloride, seawater. What goes out from the process? There are two streams going out of the process. One is the permeate, what goes through the membrane, which is our potable water, drinkable water. That contains 0.1 weight percent sodium chloride. Another stream going out of the process, another stream going out of the block is the reject stream, the retented stream, what is retained by the membrane. And obviously, because there is more water coming in the permeate side, the salt will get enriched in the reject stream or the retented stream. And let's say that reject stream or retented stream contains 8 weight percent sodium chloride. So that information I have already given to you. Block diagram I have already given to you. The next thing that we are going to do is we are going to select a basis for calculations. In this particular case, what basis do you think we should select?
1 kg of incoming water.
100 kg of solution.
Correct. So basis can be 1 kg of incoming seawater, because I want answer in terms of how many kgs of permeate we are going to get per kg of the incoming seawater. So basis is easy to decide here. It is already given, but we did not have 1 kg of the basis. Just to prove my point, I am not going to take 1 kg of basis as seawater. Let me take basis as 100 kgs of seawater. Okay, just some other basis, not what I want. I am just taking some other for the purpose of calculations. Okay, that is the second thing that we are going to do. The third thing that we are going to do is represent the information that is given in the problem, that is asked from the problem, in the form of tables. Let me tell you what I mean. So in each stream, we are going to, next to each stream, we are going to write a table of what the components are and what is their weight, what is their composition. All the information about that stream we are going to write in the form of a table next to that stream. So for example, this seawater, what is it going to contain? It is going to contain sodium chloride. It is going to contain water. Okay. What other information I have about this process is weight percent. Weight percent is 3.5 weight percent is sodium chloride. So what is the weight percent of water now? It is 100 minus 3.5%. So 96.5 weight percent. What else do I know from this stream? If I say the total my basis in terms of kgs is 100 kgs of this incoming stream. So if it is 100 kgs of this incoming stream, it will contain 3.5 kgs of sodium chloride. It will contain 96.5 kgs of water. Okay. So this table that we have drawn, or this table that we have made, this table is going to convey all the information that is required and all the information all the information that has been given about this stream. Do you agree?
Yes, sir.
Yes, sir.
Same way, we will make a table for this reject stream. Okay, let me just rub this out so that I have some place. The reject stream again is going to contain sodium chloride. It is again going to contain water. Okay. What information do we know in terms of weight percent, in terms of kgs? I know that this is going to contain 8 weight percent sodium chloride, and therefore it will have 92 weight percent of water. Do we know anything else about this stream? We don't know the kgs, we don't know the kgs of sodium chloride, we don't know the kgs of water because we don't know the total. Same way, now the permeate stream, let's make a table for that as well. The permeate stream. The permeate stream is going to again contain sodium chloride. It is going to contain water. In terms of weight percent, we said that this sodium chloride content in the permeate is 0.1%, right? And therefore, the water content would be 99.9 weight percent. In terms of kgs, I don't know anything about the quantities. That's what, in fact, I want to find out. In terms of total, I don't know what it is. Okay. So far, so good. We have represented all the information in the form of tables. Do you agree with this? So far, so good.
Yes, sir.
Okay. Now let's go forward. Now, next thing that we are going to do is start doing material balances. For doing material balance, we need an envelope over which we are going to do material balance. So just let me give you an example. So we are going to do material balance across this block, right? So we are going to do material balance across this block or around this block, and this blue thing that we have drawn around that block, we are going to call as control volume. Okay. So in this particular case, there is only one block. Therefore, the control volume and the block is the same. But soon we will go to problems where there will be multiple blocks, and then our control volume for doing material balance, maybe it may be one block, it may be 2 blocks, it may be 3 blocks, it may be 4 blocks, it may be all the blocks in the process. Okay. I will explain as we go along. All these things would be clear. So that's the 4th step we are going to do. Decide the control volume. So in this particular case, there's only one block, so the control volume and the block is the same. So the blue is our control volume for doing material balance, and slowly we will start doing control volume for doing energy balance as well. Okay. Now, for this control volume, what we are going to write, our material balance, we are going to write as amount coming in must be equal to amount going out. Do you agree with this statement? There is no nuclear reaction that is happening in the reverse osmosis process. So no mass is getting converted to energy, and therefore whatever amount is coming in must be equal to the amount going out. There's no reaction happening. There's no reaction of sodium chloride and water. Sodium chloride is not suddenly reacting to become something else. And therefore, material balance must be satisfied across this control volume. And therefore, the amount coming in must be equal to the amount going out. Okay. This material balance, amount coming in and amount going out, we can write for all components. In the process, we can write for total amount, total quantity of all things put together. Let me just give an example. So if we say 3.5 kgs of sodium chloride are coming in, then 3.5 kgs of sodium chloride must be going out. Where are they going out? They are going out in the permeate stream, and they are going out in the reject stream. So the amount of kgs of sodium chloride in the permeate stream and the kgs of sodium chloride in the retentate stream must add up to 3.5. Same way we can do a balance for water. 96.5 kgs of water are coming into the process. The kgs of water going out in the permeate stream and the kgs of water going out in the retentate stream together must be equal to 96.5. Total amount coming in is 100 kilograms. And therefore, the total kilograms going out in the permeate stream and the reject stream together added up must be equal to 100 kgs. Do you agree with that?
Yes, sir. Yes, sir.
Okay. Now, we have too many unknowns. We don't know what is going out, sodium chloride going out. We don't know what is water going out. We don't know what is the total amount going out. So let's just say, can I say that the total amount of the solution, the permeate stream, suppose this total amount is 30 kilograms. If this total amount is 30, so just have patience. Okay, I know what I'm doing is not proper. Just have patience. I have a point to make. Okay, so the permeate stream, suppose the permeate stream is 30 kilograms. What would be the quantity of retentate stream? It would be 100 minus 30. So this would become 70. Isn't it? Do you agree with this? Now, if it is 30 kgs of the one second, let me just get my calculator out. Oops, where is my calculator? Okay, so 30 kgs of this stream is going out as permeate. 0.1% of that is sodium chloride. So out of 30 kgs of sodium chloride, out of this 30 kgs of the permeate, 0.03 kgs would be sodium chloride and 29.97 kgs would be of water. Out of this 70 kgs of retentate, 8% would be sodium chloride. So 5.6 kgs would be sodium chloride and 64.4 kgs would be water. Do you agree with that? But now, is the material balance for sodium chloride satisfied? 3.5 kgs are coming in, but what is going out is 0.03 kgs and 5.6 kgs. So these two put together, it is 5.63 kgs. 29.97 and 64.4 kgs. is what is totally going out from the process. It is more than, less than, what is it? It is less than 96.5, more than 96.5.
Less than, sir.
Less than. So this amount is less than what is coming in. This amount is more than what is coming in. No, that's not possible. Sodium chloride is suddenly not generated. Water is not suddenly disappearing. So water is not getting converted into sodium chloride. So obviously this is not possible. Why it is not possible? Because of material balance. This material balance is getting violated for sodium chloride. It is getting violated for water. And why is that happening? Is because of the silly idiotic thing that we have done. What is the silly idiotic thing that we have done?
We have assumed it.
We have assumed this 30 kgs wrongly. So what is a better thing to assume?
In terms of a variable.
Yeah. So what we can do is, since this is unknown, we can assume that suppose this amount is X kgs. This amount is Y. This amount is Z. This amount is P. This amount is Q. This amount is R. So we will have 6 unknowns. We will have 6 equations we can solve. Good idea? Bad idea?
Bad idea.
Bad idea.
It can be more efficient.
Right. Absolutely terrible idea. Not just bad idea. It is terrible, horrible. Try to keep the number of unknowns as low as possible. If I know that the permeate stream is X kgs, automatically, does it not mean that the retentate stream would be 100 minus X kgs?
Yes, sir.
Yes, sir.
Right? If the permeate stream is, oops, I was supposed to write in red, 100 minus X. If the permeate stream is X kgs, the sodium chloride would be 0.001x and water would be 0.999x. If it is 100 minus X kg of the retentate, sodium chloride in that would be 0.08 multiplied by 100 minus X. And water would be 0.92 into 100 minus X. Now, by writing X and 100 minus X, I have automatically used the overall material balance of 100 kgs. So I can, to get a value of X, now I can write a sodium chloride balance. Balance of sodium chloride. What comes in? 3.5 kgs is what comes in. Right? What goes out? 0.001x plus 0.08 into 100 minus x. Somebody solve this for x. Solve this for x. Somebody is solving or not solving?
Sir, 56.9.
56.96 kgs. Okay. We could have taken balance for water. What is coming in? 96.5 kgs is coming in. What is going out? 0.999x plus 0.92 multiplied by 100 minus x. This also would have given us the same answer. Just check, calculate for yourself and check that we are getting the same answer. Check for yourself and tell me that we are getting the same answer or we are not getting the same answer.
Yes, sir, we are getting this.
Right.
So we had a doubt in one of the homework sums that you had given.
Oh, okay. Wait a second. Let us complete this and then we'll go back to the homework sum. Okay. I mean, that's why I asked you in the initially only that if you have any doubts in the other things. Okay, anyway, it doesn't matter. We'll address that. Okay. Right. So this is how we are going to solve our problems. Now, have we got our answer? No, we have not got our answer. We have got a value of x. X is 56.96. Where is that? X is 56.96 or 56.9 or 57 if you want. So these are approximately 57 kgs. What did we want? We want kgs of permeate per kg of solution. What have we got? 57 kgs per 100 kilograms. So if I take 1 kilogram, this would become 0.57 kilograms. Right? So irrespective of the basis that you take, you are going to get the same balances. You just have to write the answer in whatever form it is required. So these are the steps that we are going to follow for all our problems henceforth. You may have done this problem in 30 seconds and I have taken more than 15 minutes, 20 minutes to explain. But as we go to more and more complicated problems in the next couple of classes, the utility of writing a process or drawing a process block diagram, writing a basis, representing the information in the form of tables, taking control volumes and doing the material balance on that control volume. This methodology that we have seen, we are going to follow that for all the problems. Okay, you will see the importance, you will see the utility of this methodology as we go towards more and more complicated problems. Okay, so what is the doubt in the homework problem?
So the answer of the second question is not matching for us.
Second means which question? I have no idea what a second question is. Now this is what I have opened. So tell me which is the second one.
Sir, acetic acid solution is taken. We have added NaOH in that.
Let me just see where it is. Did I write down here somewhere?
It was the last slide.
This one?
Yes, sir. The B part.
B part. We have acetic acid solution. We make pH equal to 4. What would be the dissociation of acetic acid? Oh, okay. Oh, this problem we want. What is the issue in this problem?
So the answers are not matching.
Not matching means what is the answer?
So I have got an answer that Ka would be 4.14 into 10 to the power minus 7.
Now, what is the pKa value that you have taken?
So we had to find dissociation, right? So
No, but dissociation.
I've taken pK as 4.75.
Correct. So pKa you have taken as 4.75. Whoever has another solution, his pKa is matching or not matching?
I got the answer as 15% dissociation. by
No.
4.75
With
pK.
4.75, you are getting 15% dissociation. Somebody else got a different answer?
Yes, sir. I got a pK of 6.383.
pK is 6.3.
Yes, sir.
Where did you get pK 6.38 from?
So as stated in the problem that we add NaOH,
Uh,
so I considered the change that it would form a buffer, and then I solved accordingly for the pK.
no. Where did we say we add NaOH?
So it's not written, but you stated to
No,
make the
no.
pH closer.
This is the second problem. We have made pH 4, right? But that
Yeah.
pH 4 we can do anything, right? But it does not change the pKa. pKa is fixed, right? pKa is for a particular component, isn't it?
Okay.
Do you agree or do you disagree?
Sir, it is coming till 15%.
No.
15.
Wait a second. Wait a second. Wait a second. There is no hurry. Let us not do anything in hurry. So if I just go to Google, if you look at Handbook of Chemistry and Physics, so if you just say pKa of acetic acid, you will get a value, right? 4.75. Now, what is that pKa? That pKa is nothing but equilibrium of dissociation of acetic acid dissociating as acetate ion and H plus ion. So dissociation constant, if I write, that is CH3COO minus and H plus divided by the undissociated acetic acid minus log to the base 10 Ka is 4.75. It is independent of what is the pH, how we have got this pH. Do you agree with this?
So,
This
but
is
if the
Oh,
pH is
understood.
given, if the pH is given in the sum, then H plus concentration is 10 raised to minus 4.
Yes,
And
I'm coming to that. I'm coming to that. All I'm saying just now is Ka is the equilibrium constant for this reaction. That equilibrium constant is independent of what pH is, whether pH is 5, 9, 6, 10, 12, 100, million, 0.00001, irrespective of minus 35, irrespective of the pH, the equilibrium constant is the same. Do you agree or do you disagree?
Yes, sir. I understood where my mistake
No,
is.
no, it's okay. It's okay. You may have understood, but there may be 35 others who are listening who may not have who may be stuck but are not able to understand where they are stuck. Okay, so let me just explain. Doesn't matter. So if log to the minus log to the base 10 Ka is 4.75, that means Ka is 10 raised to minus 4.75. Okay, so the equilibrium between the acetate ion and the H plus ion and the undissociated acetic acid, this value is 10 raised to minus 4.75. All right. Now what are we given? That we are given that this solution has a pH equal to 4. If pH is 4, that means H plus ion concentration would be 10 raised to minus 4. Isn't it? So suppose I say we start with 1 mole in the solution of acetic acid, which means 1 mole in the sense that if you find 1 mole, it is difficult, you are finding it difficult. Suppose we take 60 grams of acetic acid, dissolve in water and adjust the pH to 4, right? That means 1 mole of acetic acid we have taken, 1 gram mole of acetic acid we have taken, right? So in the solution now, so suppose this is your solution in a beaker, okay? What is this solution going to contain? It is going to contain water, it is going to contain H plus ions, it is going to contain OH minus ions, it is going to contain undissociated acetic acid, it is going to contain acetate ion, right? Maybe I have added NaOH, that's why it is going to contain Na plus ion as well, right? Do you agree with that? These are the things that are going to be present in this solution. What did I start with? I started with 1 mole of the acetic acid. So suppose I say X gram moles have dissociated. This acetate ion and the undissociated acetate ion, the acetate ion and the undissociated acetic. So gram moles of acetic acid and gram moles of the dissociated acetate ion, this put together must be equal to 1, because I have started as 1 gram mole. I started with 1 gram mole and then adjusted the pH. Do you agree?
Excuse me, sir. Please could you explain this part again?
Suppose I have a solution. I have water. Suppose I have water in a beaker and I take 60 grams of acetic acid. I go to weighing scale. I take out 60 grams of acetic acid, weighing balance. I measure 60 grams of acetic acid and I put that in this water. Acetic acid will dissociate. Now I want pH to be equal to 4. So I will take a pH meter. I will put the pH meter inside, or I will take a pH paper. I will keep on adding sodium hydroxide till pH becomes equal to 4. Right? So now
Yes, sir.
this water that is there in the solution, the beaker that is there, it is going to contain water. Water also is going to dissociate. It is going to have H plus ions and OH minus ions. Acetic acid, the initial 60 grams, 1 mole of acetic acid that I have taken, there will be some acetate ions as well. Suppose I have taken sodium hydroxide for neutralization, I will have Na plus ions as well. Isn't it? So there are neutral species in the solution. Neutral species are water, acetic acid. There are positively charged ions in the solution, and there are negatively charged ions in the solution. Do you agree with that? But because I have taken 1 gram mole initially, the moles of acetic acid undissociated plus moles of the acetate ion that have formed, this must be equal to 1. It has to dissociate into acetate ion and H plus ions. So if I say X gram moles have dissociated, the acetic acid that is left will be 1 minus X gram moles. The acetate ion would be X gram moles. I have adjusted the pH, so H plus ion concentration would be 10 raised to minus 4. So hydroxide ion concentration would be 10 raised to minus 10. I don't need all these. I don't need Na plus concentration, not required. I'm not asking you for that, isn't it? But there will be a Na plus ion if I'm using sodium hydroxide. If I'm using ammonium hydroxide, it will be ammonium hydroxide. If I'm using HCl, I will have H plus ions and Cl minus ions. So whatever else I have used for making neutralization. But now if this solution has volume of this solution is 1 liter, now I can write this equilibrium. Ka would be the acetate ion concentration, H plus ion concentration, and the undissociated acetic acid concentration. This must be equal to 10 raised to minus 4.75. If the solution is 1 liter, the acetate ion concentration would be X. H plus ion concentration would be 10 raised to minus 4. Acetic acid undissociated would be 1 minus X. This would be equal to 10 raised to minus 4.75. Can we not solve for X? Yes, no, do you agree? Do you disagree?
Yes, sir.
In fact, you can do it for different pH values. Suppose pH value was 1. If I add HCl and I adjust the pH to 1, or if I add H2SO4, adjust the pH to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14% dissociation. For this particular problem, you will get X from solving this, isn't it? If your pH is 2, your X would be X into 10 raised to minus 2 divided by 1 minus X would be equal to 10 raised to minus 4.75. If your pH is 8, it would be X into 10 raised to minus 8 divided by 1 minus X would be equal to 10 raised to minus 4.75. This will be fraction dissociated because we have taken X as fraction out of that 1 mole. Multiply that by 100, I will get percent dissociation. If your pH is 12, X into 10 raised to minus 12 divided by 1 minus X would be equal to 10 raised to minus 4.75. So you can calculate degree of dissociation for any pH you want. Now that pKa is 4.75, if you had taken 4.75, then what would we have? X into 10 raised to minus 4.75 divided by 1 minus X would be equal to 10 raised to minus 4.7. This means X would have been 0.5. That means X would have been 50% dissociated. That's the meaning of pKa, right? At that pH, 50% is in the dissociated form. 50% is undissociated form. If you go to higher pH, 5, 6, 7, 8, 9, 10, then the dissociation will increase. It will become 60, 70, 80, 90, 100, 99.999999. If you go to lower pH, dissociation will reduce. 50 will become 20, 30, 20, 10, 1, 0.1 and so on as you go to higher and higher pH. Is that okay?
Yes, sir.
Yes. Can we go to the next problem now? Or you want a break of 5 minutes? Do you want a break of 5 minutes? Or shall we continue?
Sir, a break would do.
Yeah, just a break of 5 minutes. So we'll reassemble at 9:40. We'll reassemble in 5 minutes, 9:40 as per my watch. Your watch may be a little different here and there. Okay, let's take one more problem so that all things would be just again reinforced. Let's say we have a pharmaceutical compound, and let's say that is dissolved in water. So we have a solution, aqueous solution, containing 5 weight percent P. Okay. We would like to concentrate this solution so that the concentration of P goes up. We would like to concentrate the solution to 50 weight percent P, aqueous solution. So how would we do this? One of the ways is to put it to an evaporator to evaporate the water. So when water evaporates, let's assume that only water is evaporating. There is no P in this evaporated water. Do you agree? Yes, no?
Yes, sir.
Yes.
So what I want you to calculate kgs of water to be evaporated per kg of 50 weight percent P per kg of the product. Per kg of this solution coming out of evaporator. Okay, is the problem statement clear? I wanted to tell me how many kgs of water is evaporated per kg of this product solution. This contains 50% coming out of the evaporator.
Sir, 9.
Okay, so let's do this. So answer, frequency. So 9 is one answer. Obviously, problem seems very simple.
Sir, could you please repeat the question?
Question is, there is an evaporator. We have an aqueous solution containing 5-8% P. We are sending it to evaporator so that we can concentrate that P in that solution to 50 weight percent. That is what is going to come out. One of the ways in which we are going to do is, if you evaporate water, automatically the concentration of P will increase. So we are going to send it to an evaporator, and that evaporator will evaporate water. No P will go there. What I wanted to calculate is the amount of water to be evaporated, kgs of water to be evaporated per kg of the solution coming out of the evaporator.
Sir, 9.
Okay, 9 is one answer, and there's one more answer. 2,
Sir, 9.
3,
Sir, 9.
4. Seems very simple.
Sir, 9.
Sir, 9.
Any other answer? Very straightforward. Anybody stuck? Anybody wants me to solve and show the solution? We'll give you 5 to 3 more minutes. We have 7 answers so far. has not answered?
9.
Swaroop. Oh, there are 3 Atharvas in the class. Atharva Punde. Can you answer?
I said 9.
9. Oh, you already said. Oh, somebody who has not said. Gauri Dhumal. I'm just taking names at random.
So just one more minute.
Okay. Take your time.
Sir, 9.
Okay. Om.
Yes, sir, 9.
Sarthak.
Sir, 9.
Okay. Craig D'Souza.
So the answer is 9.
9. Ria. Okay. Right. So many people are getting 9. Gauri, shall we go forward?
Yes, sir.
Shall we see the solution or it is straightforward?
No, it's straightforward.
It's straightforward. Okay. There's just one point that I want to convey. Okay. We will modify this problem. We will modify this problem. Okay. Same situation. Aqueous solution containing 5 weight percent P. Instead of it going to one evaporator, it goes to first evaporator, then it goes to second evaporator, then it goes to third evaporator. You may think it is silly. Instead of using one evaporator, sorry, you may be thinking it is silly that instead of using one evaporator, why we are using 3 evaporators. But just wait till July, we will know why 3 evaporators. So now we have 50% by weight. Some water gets evaporated here, some water gets evaporated here, some water gets evaporated here. Okay. I want you to tell me how much is the weight percent P in this solution, how much is the weight percent P in the solution coming out of the second evaporator. I'm going to tell you that the amount of water evaporated equal amounts water get evaporated in each evaporator. Okay. Is the problem clear now? Problem statement is clear. Same problem as earlier. We have a feed that is containing 5 weight percent P. We have a product solution going out that is 50% by weight P. But instead of doing it in one evaporator, we are going to use 3 evaporators. Equal amount of water is going to get evaporated in each evaporator. So earlier, this whole thing was one evaporator. Okay. Now, instead of one evaporator, we are having 3 evaporators. And equal quantity of water is getting evaporated in each evaporator. I want you to calculate what is the concentration of P in the solution leaving the first evaporator. This is what I want you to calculate. I want you to calculate what is the concentration of P in the solution leaving the second evaporator. Okay, that's what I want you to calculate.
Sir,
Excuse me, sir.
first weight percent of P is 7.14 and second is 12.5.
7.14 and 12.5. That is
Yes,
what?
sir. I am also getting
Yes.
same.
7.14 and 12.
So Praveen, Nishant, 7.14 and
Yes, sir. 7.14 and 12.
Ansh also is the same. We'll wait for Gauri.
So 7.14 in and 12.5.
Same answer?
Yes.
Atharva gives the same answer. Gauri, when you finish, tell us. Who else? Mayur, have you finished? Mayur, are you doing? Do you need more time?
Yes, sir. Same answer.
Ah, okay. You are very quiet. You don't respond. Pihu. We'll wait for Pihu to answer.
Yes, sir.
Same answer. Okay. Shivam Jadhav.
Yes, sir, same answer.
Shivam, are you there? Shivam, answer. Shivam, are you there? Not there? There's just one small point I would like to convey, and that's why we are going to see the solution. Okay. Again, the methodology is the same. Process block diagram. We are going to take basis. What basis would we want to take here? So this is
Standard sum of H2.
P and water, kgs, weight percent, P and water, kgs, weight percent, P and water, kgs, weight percent, P and water, kgs, weight percent. Can we take basis as 100 kgs of the feed coming in? Okay, so if this is the basis, this is 100, then obviously what do we have? We have what else we know? We know this is 5 and this is 95. We know this is 50 and this is also 50. So if this is 100 kg, then P would be 5 kg, water would be 95 kg. Now here is what I want to emphasize. Okay. Suppose I take this whole plant as a control volume. So our control volume is this red block. So it does not matter what is happening inside. Across this whole block, this aqueous solution of P is coming in 5-8%. Aqueous solution of P is going out 50-8%, and water is going out. Water is going out of this control volume. From the first, water is going out from here, water is going out from here. So now if I do sodium chloride balance on this red control volume, if I do if I do sodium chloride balance on this the red control volume, 5 kgs of sodium chloride is coming in, no sodium chloride is going out here, no sodium chloride is going out here, no sodium chloride is going out here. Sorry, not sodium chloride. In this particular case, it is P, right? So 5 kgs of P is coming in, no P is going out in this stream, no P is going out in this stream, no P is going out in this stream. So all the P must be going out from this 50% by weight stream, and therefore the P going out of that stream is 5 kgs. Now if P is 5 kgs and the concentration of P is 50 weight%, that means the total must be 10 kgs. And if total is 10 kgs, P is 5 kgs, this water must also be 5 kgs.
Sir, can you repeat once again?
Okay. Let me repeat. Now we are going to take a control volume. So let us take this whole plant as a control volume. Do you agree with that? Now, if I write a balance for P, the 5 steps that we are doing, we have selected a block, we have drawn a block diagram, we have selected a basis, we have represented the information in the form of tables, we have taken this red control volume. Now we take balances across this control volume, the 5th step. Okay. So if I take a balance for P, 5 kgs of P is coming into this red control volume. No P is going out along with this water. No P is going out along with this water. No P is going out along with this water. P is only going out in this stream. So whatever 5 kgs have come in, all those 5 kgs have to go out from here. Sarthak, do you agree? You had asked, right, Sarthak? Who was asking?
Yes, sir. Yes, sir. Got it, sir.
Got it. Okay. Okay. This, the component P, has allowed us to write this material balance across this red control volume. So now P is 5 kgs and P in this solution is 50 weight%. That means the total must be 10 kgs. And if total is 10 kgs, water must be 5 kgs. So our solution problem has been solved by a fact that this component P is not changing across the control volume. We are going to call that as tie component. Something that is not changing across the control volume. That has allowed us to do the material balance for water and calculate the amounts of water and weight% of water. Same way now, if I take not this red as a control volume, oops. If I take this blue control volume, now by material balance for P, we can straight away say that this 5 kg is going to remain unchanged. If I take this green control volume, again I can say this 5 kg is going to remain unchanged. If I take this gray control volume, then by material balance we can say that 5 kgs is coming out. So our control volume can be blue, our control volume can be gray, our green, our control volume can be gray, or our control volume can be red. Right? So the control volume is different from the blocks. It can be one block, it can be multiple blocks. So now if I take this red control volume, now I do balance for water, 95 kgs of water are coming in from this control volume. Some water is going out here, some water is going out here, some water is going out here. 5 kgs of water is going out here. So that means 95 minus 5, 90. 90 kgs of water must be getting evaporated in the evaporator. And what I have told you is equal amounts of water are getting evaporated. So in this evaporator, 30 kg of water must be getting evaporated. In the second evaporator, 30 kgs of water must be getting evaporated. In the third evaporator, 30 kgs of water must be getting evaporated. Do you agree with that? Sarthak?
Yes, sir.
Now if I take now if I take this blue control volume, now I do balance of water, 95 kgs of water are coming in, 30 kgs of water are getting evaporated. That means 65 kgs of water must be remaining, coming out of the first evaporator. So the total must be 70 kgs. If I take the green control volume, 65 kgs of water are coming in, 30 kgs of water are getting evaporated. So 35 kgs of water must be coming out of the second evaporator. If I take the gray control volume, 35 kgs of water are coming in, 30 kgs are getting evaporated, 5 kgs are going out. That is correct. So blue control volume plus green control volume plus gray control volume is the same as our red control volume. So the weight percent now coming out of the first evaporator, weight percent of P would be 5 divided by 70 into 100. Weight percent of P in the second evaporator would be 5 divided by the total 5 plus 35, 40 into 100. Okay. Do you agree? Do you disagree? Anybody has any doubts? Sarthak, any doubt?
No, sir. Got it, sir.
Gauri, any doubt?
No, sir, got it.
Jairaj, any doubt? Rushikesh, any doubt? I'm just taking
No,
something
sir.
at random. Vaishnavi, any doubt?
No, sir.
Okay. Clear? Now here is a problem. Shall we go to the next problem?
Sure, sir.
Yeah. Any doubt? Or yes, we can go to third problem. Want a simple problem or a complicated problem? Want a simple problem or a complicated problem? Somebody say something. You want a simple problem or a complicated problem? Nobody is saying anything.
Sir, medium level.
Medium level. All right. So, you know, I will let you in on a secret. Whatever you would have told, I would have given the same problem. And I would have said it is simple problem or a difficult problem or a medium problem. I'm just joking. Don't take me seriously. So imagine that there is a pipeline. You have done engineering graphics. right? So you know. So this is a pipeline. Okay. So the gas, there is a, let's say, natural gas. Assume that natural gas is 100% methane. Okay. Oh, sorry. Let's not assume it is 100% methane. Let's assume it is going to contain methane and carbon dioxide only. Okay. So let's say methane and it is carbon dioxide. Okay. So let's say this natural gas is containing methane and carbon dioxide. So let's say it is, let's just take some numbers, 0.8 volume percent carbon dioxide and rest methane. Okay. So let's assume that this natural gas is at 35 degrees centigrade and pressure of, let's say, 450 kilopascal absolute. Okay. Now, if I want to measure the amount of gas flowing through this pipeline, one of the ways is I add carbon dioxide here and I measure the concentration of carbon dioxide coming out of that pipeline after some distance. So let me reduce the size of the pipeline just so that I can do the problem. Right? So if I add pure carbon dioxide, what will happen to this concentration of carbon dioxide coming in and going out? What will happen?
Increase.
Increase. So let's say it becomes 1.1 volume percent carbon dioxide. I have not added anything else, so rest is methane. I have added pure carbon dioxide. Now, what I want to do is I will measure how much pure carbon dioxide I am adding. Because I am adding that, I can measure that accurately. I will measure this increase in the composition of carbon dioxide. Okay. That will allow us to allow me to calculate how much is the gas coming in. Okay, so here is a problem. So, okay, let's say the amount of pure carbon dioxide that we have added is, let's say, 2 liters per minute. Okay. 2 liters per minute is at 50 degrees centigrade. And let's just take some pressure, 520 kilopascal absolute. All right. I want you to tell me how many liters per minute of this gas comes in. Okay. Will you be able to solve? Do you want me to repeat the problem?
Yes, sir.
Yes, sir. Yes, sir.
There is a pipeline. In that pipeline, let's assume that there's some long pipeline. So many other things are also happening in the pipeline. Let's not worry about that just now. Okay. I have some gas coming in, natural gas coming in. Natural gas, let's say it contains 0.8 volume percent carbon dioxide. The rest is methane. I'm adding certain amount of gas, pure carbon dioxide gas. I am adding that out from outside. I'm adding 2 liters per minute, which is at 50 degrees centigrade, 520 kilopascal absolute pressure. This gas that I add and the gas that is coming in, these gases get mixed, and the concentration of the carbon dioxide going out from this pipeline after some distance, after they mixed together, is 1.1 volume percent carbon dioxide. Okay, I have measured this. I have measured this composition, it is 1.1. I have measured this inlet composition, it is 0.8. I have measured that I have added 2 liters per minute of this gas. I want you to tell me how many liters per minute of this gas is coming in to this pipeline. Okay, is the problem clear?
So, sir, we have to calculate for the natural gas, na? Not the
Yeah.
CO2.
What is coming in? Whole natural gas is whole of 8.8 volume percent CO2 and 99.2 volume percent methane. This whole thing is called as natural gas. I want you to tell me what is the total quantity of natural gas that comes in terms of liters per minute. Understood? Yes or no?
Yes, sir.
In terms of liters per minute. This is your what you have to calculate. Okay, let's solve. 10-15 मिनट में खत्म हो जाएगा। हाँ, 10-15 मिनट में खत्म हो जाएगा मेरा। चलो 10 मिनट। हाँ सुयोग। हाँ मी आहे इकडे ऑफिसला. माझं लेक्चर चालू आहे, मी त्याला 11:30 पर्यंत थांबवतो, मग 10:30 ला करून येईन. ठीक आहे. हाँ ठीक आहे. मी तर 8:30 ला बघतो. ओके बाय. कल ना मैं चालू किया ना कंप्यूटर, मैं इधर गया दूसरा काम करने के लिए। आया तो देखा धीरे डबल कर पानी गिर रहा है। पूरा ट्रेन नीचे से गिरा है ना? हाँ पूरा नीचे गिरा है। अरे इधर 10 मिनट ठीक है, चलेगा। कितना टाइम लगाओ? मैं ऐसे ही करूँगा। फिर ये कॉल करना फौरन आ जाऊंगा और तुम्हें नंबर देता हूँ आपको। ये नंबर दे दो, नेक्स्ट वीक में आपका What is the point?
This is it. This is it. I also want a signature by that 20.
Here I will say.
Here, anywhere on this. As they require the hard copy of this, so I did it.
This also.
And here, second page over here.
This is common.
Yes. Autoclave is there actually. AMC.
AMC.
Yes.
Yeah. Okay. Any answer?
Sir, 659.3 liters per minute.
659.3
9.3.
okay. Liters per minute. You are telling me, no?
Yes, sir.
Yes, sir. 6.59. 659.6, sir.
Yeah. Forget that point.
Sir, 6.59 liter per minute.
Mahesh, you are saying 6.59 or 659?
6.59.
6.59. Very nice.
Sir, 659.
659. Oh, sorry.
Sir, this
Sorry there. Yeah, first one. Why don't you put your profile pictures? I will know at least how you look like. And I will know that you are not bots. Bots can't solve problems, but well, one of these days AI is going to be powerful enough to solve these kinds of problems. Shaurya Raj.
Sir, 659.
Yes, sir.
Ria has said 659. Mahesh has raised a hand. Mahesh, go ahead. Don't bother raising a hand. Just unmute and ask.
Sir, it's by mistake.
It is?
It's by mistake.
Oh, so 6.59 is not the answer?
No, I am raised the hand by mistake.
Oh, raise the hand by mistake. Oh, sorry. So Mahesh is correct. All others are wrong. Or all others are correct. Mahesh is wrong. Till we get some more answers. Aditi, answer. How did you people get this answer so quickly? The very fact that you got these answers so very quickly tells me that there is something wrong with all these answers. Okay, so whoever has got, Mahesh, let's talk to Mahesh. Mahesh, you got answer 6.59, right? How did you calculate?
Sir, I assume that X liter per minute of natural gas is coming in.
Okay.
So 0.8x carbon dioxide is coming in.
0.008, 0.8 it is.
0.8%.
So 0.8 is 0.008.
I did that mistake, sir.
Okay. 0.008x plus what? What did you do?
Plus 2 incoming carbon dioxide.
Is equal to what?
Upon 2 plus 0.008 x plus 99.2x methane. I have calculated the final percentage.
Okay. So you have said that this is x. So what goes out is x plus 2, isn't it? And that x plus 2 is 1.1 volume percent. Now if I do carbon dioxide balance, what carbon dioxide out of this x.2, what carbon dioxide goes out is 0.008 plus x. So sorry, 0.008 x plus 2 is the carbon dioxide. Let's do one thing. Let's do properly carbon dioxide, methane. So you are saying this is x. So this is 0.008x and this is 0.992x, right? So now this is carbon dioxide and methane. This is x plus 2. So this is 0.011 into x plus 2. Isn't it? That's how you're done, right?
Yes, sir, but I have taken 0.8 and 99.2.
That is okay.
That's my mistake.
That is okay. So this is 0.989 into x plus 2. Right. So now the balance that you have done, 0.008x plus 2 must be equal to 0.011 into x plus 2. This is the balance that you have done. You have made a calculation mistake, but that's okay. But the balance that you have done is like this, right?
Yes, sir.
how many people think this is right? How many people think this is wrong?
Sir, the volume won't be same. It is not additive.
Karthik, whenever you come to ICT, meet me, I will give you a chocolate. So only Karthik is right. Everybody else is not right.
So should we convert it into moles and then calculate?
Volume in plus volume added is not equal to volume going out. Why not? Because the temperatures are different.
Temperature and pressures are different.
Pressures are different. So we are not going to write a balance for volume. Never, ever. Oops. Never, ever. What is conserved? Moles. Moles of carbon dioxide coming in plus moles of carbon dioxide coming in must be equal to moles of carbon dioxide going out, or moles of methane coming in, no methane is added, must be equal to all the methane moles that are going out, or kgs of carbon dioxide coming in plus kgs of carbon dioxide getting added must be equal to kgs of carbon dioxide going out. Right? So solve this problem properly. Either you convert everything to moles, you convert to kgs, whatever you like, whatever is your favorite.
So what is the final temperature and pressure, sir, for the 1.1?
I have no idea. Somebody who was doing this experiment forgot to measure temperature and pressure. So now tell me, how many liters per minute come in? Either you can say this idiot forgot to measure temperature and pressure and therefore we can't solve the problem, or you say that we don't need this temperature and pressure. Some young kid, 11th standard kid, was doing this experiment, and this kid forgot to measure the temperature and pressure at the outlet. Your kids, no? We can excuse them from doing silly things. Now you are grown-ups. Soon you are going to be 80% engineers at the end of this course, or at least 80% of the concepts of chemical engineering we are going to cover. So all those who had got answers so quickly, you had done a balance of volumes. Yes or no?
Yes, sir.
Yes, sir.
See, be careful. Some of you seem to be Manchester United fans. They finished second, right, in the Premier League?
Yes, sir.
They always score goals in the 90th minute. They never score goals in the first half. Ever notice that?
Yes, sir.
I know. What is the weird thing they do? So all Manchester United matches, just watch in from 85th minute onwards. Nothing happens till that time. You can save 85 minutes and devote that 85 minutes to doing material balance.
Okay, sir.
I would urge you to put your photographs there so that I know that in case you come to ICT, I will know that who you are. Not just you, others as well. Only Arya has put his photograph. Oh, some others people. Oh,
So that is also old. Like
oh, that's an old
when I was-
photograph.
Yeah.
Oh. What, school photograph? 10th standard, 11th standard?
No, sir. About 2 to 3 months ago.
But 2 to 3 months ago. By that standard, it's not old. So my photograph is 3-4 year old.
Sir, but my hair are gone. I had long hair before.
Oh, now your hair are not long. Okay.
Yeah.
Snehal has put photograph. Nice. Anirudh has put photograph. Mayur has put photograph. All right, will you be able to solve this problem? Do this as homework?
Yes, sir. We'll do this.
Okay, sir.
Okay, sir.
Yes, sir.
Now, couple of points is when you get an answer, don't wait till the next class to know whether it is the right answer or wrong answer. Right? You can put in your informal WhatsApp group or you can put it in your formal WhatsApp group, and other people can say that this is not what I got. You can share your solution in WhatsApp and somebody can check your solution. So use social media for communicating answers. And sharing solutions. Okay, so that is one point. So next class we will see this solution in maybe few minutes, but let's not spend too much time on that. Let's use the advantage of social media to get the concept across. That's the first point. One more point I had was about continuous assessments. So in the continuous assessments, we will have M quizzes. We will take N best out of them. And then we will scale to 30 marks. And let me just say that M minus N will be at least greater than or equal to 1. Right? So don't worry if you have missed a quiz. Maybe it is 1, maybe it is 2, maybe it is 3, maybe it is 4, maybe it is 5, maybe it is 6. And so even if you miss, let's just say, even if you miss a quiz, don't worry about it. Okay. That is the second point. Third point is some of these quizzes are going to be based on Google. All are going to be based on Google Classroom, Google Sheets, or Google Forms. So when is a good time to have a quiz? Arya, when is a good time to have a quiz?
So whenever you feel better, according to that, I'll let you know.
No, I feel good time to have quiz is every day, but that's not feasible. Then I feel good to have quiz every week, so that's feasible. But on Tuesday, immediately after my lecture, you have a lecture, and same way Thursday, immediately after my lecture, do you have a lecture?
No, so that is a break, I guess, on Thursday after your lecture.
Okay, so perhaps what we can do is I will assign the quiz at the end of the class on Thursday, and then you can turn it in within the next 1 hour or so. Okay, so whatever is the end time. Okay, so anyway, I will I will tell you on Thursday.
Yeah. Sure, sir.
But don't worry about the quizzes. Can anybody tell me what is the purpose of the quiz?
For our understanding, they have understood it.
What is the purpose of the quiz? Do you think it is to give continuous assessment marks?
No, sir.
No.
So that at least we are up to date with what we are learning.
Absolutely. So that is not the purpose of giving quiz. Purpose of the quiz is to make you aware whether you have learned concepts. That is the only purpose, to make you aware, and therefore answer honestly. Don't copy. Don't ask others. Not that it helps, because everybody may get a wrong answer. Okay? That is the only purpose of having quizzes. Okay? Not to give you continuous assessment. Continuous assessment, everybody will get good marks. All right. So we'll stop here for the day. Solve this problem by Thursday, and we will very quickly see the solution. But before that, you should all be sharing the solution amongst yourself, asking each other whether the solution is right or wrong. Not asking whether the answer is right or wrong. Ask others whether the method of solving and the values, the numerical values at different steps, whether that methodology is right or wrong.